Hello again. Another example for cantilevers. So example 2, draw the shear force and bending moment diagrams and label values at point of interest for the following beam or cantilever. Just ignore the weight of the beam in this example. Previously, we solved the cantilever with two forces away from the fixed support or the cantilever. And now we'll have one force, another one is a UDL, 3 kilonewtons per meter. And that value is about 3 kilonewtons per meter, even it's covering 1 meter. So let's see how this will act in the shear force and bending moment diagram. We start the examples as usually. So inserts, and step 1 is, as we used to say, free body diagram for it. So what we have at point A, this is the only support reaction we have, then we can replace that by two forces, one in the X direction and the other one in the Y direction, and a moment around that point. So this is the force, which we could call it AX, AY, sorry. Sorry. And there is a force acting on the X direction, which we'll call it AX. And there is a moment, we will assume it, again, similar to the previous example, it's going kind of anti-clockwise. We call it MA. Just minimize the size of the A here, so it doesn't look like one, right? And then I don't need to keep that like area because that's showing just the free body diagram. Now, second step is to calculate support reaction forces. So find the value for AY, AX, and MA. As you can see in the previous example, there is no forces acting on the X direction. Therefore, summation of forces for X so if X equals to 0, and this leads to AX equals to 0 because it's not active. Sorry for that. Now, summation of forces in the Y direction equals to 0, and this will lead to AY is going up. Against that, what you have the 10 kilonewtons plus the 3 times 1, which is the UDL. This will give 13, or let's make it in a better way, AY equals to 13 kilonewtons. Just the font there looks a bit tiny, so we'll increase the size for it. Oh, maybe that was too big. Cool. So again, because we need to be aware of the direction, positive and negative, so for this X direction, this is the positive, and for Y, this is the positive. Now we need to calculate the moment around point A. So we come to this equation. So we enter the equation editor, algebraic summation of moment around point A equals to 0. So what do we have there? The first thing we have, we start from one end and goes to the other end. So the UDL, it's acting in the middle. So it's 3 times 1, so right, 3 times 1, that's as a force, times what's the distance? The distance is 3 plus 1, that's 4, and half of that distance. So kind of the UDL acts from the center for it and going to half, and that will be the distance. It's, I'll write it 3 plus 1 plus 0.5. This is as a distance. What else you have? This is going as a positive clockwise. So clockwise is the positive, plus you have the 10 times 3. All of that equals to MA, which is the opposite direction for it. Because if we assume everything here is a clockwise, then I just need to indicate the direction. So that's my rotation. That's not clockwise. I need to find the direction for clockwise. This one. Okay. After using your calculator and adding everything together, you'll find MA equals to 43.5 kilonewtons meters. So this way we managed successfully to calculate the value for MA. So I highlight these values to make sure I know them and I need to use them some stage. It's very good to be very tight and showing all the results. Now step 3, I need to sketch the shear force. So what we learned that we extend the lines where we believe there will be a good impact or information we need to investigate. And that's happened exactly the same thing for the UDL. So I'm adding another disconnected line where is the centroid for that UDL. Also, I need to have my reference point. So I would just sketch a line where will be my reference point we're trying to achieve for the shear force. Don't forget to label the shear force. So step 3, shear force, unit is kilonewton, and we're trying to find it here. It's very easy to start from AY. So AY is positive value, 13. So I move up around 13. If you do it with a scale, it will be really very good and precise. But since I'm not using any scales, because since I have limitation in my PowerPoint, so I'm not related on that other stage. But if you use a graph paper, you get everything to scale. So that will be reading 13 as a kilonewtons. I don't need to put the units since I labeled this as shear force. Now, if you look carefully from that point, there is no force acting till you reach to the point where is the 10 kilonewtons. So 13 minus 10, take me down, that will remain 3. I'll go up about this point and then copy this number and say this is a 3 kilonewtons. Again, there is no change in the structure of the shear force diagram till I reach to the point where is the UDL. The UDL is about this point. Now here is interesting what's happened. I know here is 3 based on that value, how much I can go to that point. So how can you achieve that? Is just by multiplying 3 times 1 is 3, and 3 minus 3, because the direction of the UDL is going downwards, this will result to equals to 0. So from this point, I need to go as a slope as I explained late in the class on Monday. And then you come here and then you just close that to 0. Make sure to write that this is where start getting 0, since the scale is very difficult. So just point this point is 0, actually, is 0 shear force. It's very important to show that in your shear force diagram. So again, if you look carefully, what we created is showing to us this is my positive area. And also, I have a positive area here, and there is also a positive area here for the UDL. Now, as interestingly, both areas they are representing positive for us, which is really good. But the difference between previous example, as soon as we change from point load to UDL, what's happened here, instead of force going downwards, it became as a slope. So kind of it is a linear function. One is a constant function. This one is a linear function. If we continue to try to find the bending moment diagram, so step 4, I'm just copying this and then we'll edit them very quickly. So 4, that will be bending moment, and kilonewtons meters the units. Very important to specify the units. So the moment we got is 43.5. I'm sketching this as a clockwise, so this one is actually anti-clockwise, so it's going negatively downwards. So I will bring this down, and then we'll put the value, which is minus 43.5. Don't need to write the units because it's already specified in the diagram. Now, what's interestingly here, guys, I have a positive area. So I will show you the calculation on the side so you can understand how we can find the rest of the values. So minus 43.5 plus, because it's a positive area, 13 times what? Times the distance 3. This will give you minus 4.5. Then from this point, I will go to something very tiny till this point, and will be minus 4.5. Now, also what I have from this point, I come here back and I say minus 4.5 plus, because it's a positive area, 3 times 1. That equals to minus 1.5. So I will continue with another slope, but goes till this point. Technically, it's not 0 yet. And if you have it on a scale, you can see it better than what you can see here, 1.5. Now, the last one is not anymore rectangular. So minus 1.5, and this one would be plus because the area is positive. Now we have half of the base, which is the base is 1. Half of it is 0.5 times the height, which is 3. So it's 3 divided by 2 is 1.5. So minus 1.5 plus 1.5, that is equals to 0. Very easy. Now here you need to be a bit careful, because that's technically will not be anymore as a slope, would be kind of a curve. So kind of will be closing the diagram in this way. I'm trying to make it as much as I can, but it's actually sometimes very difficult to achieve that with this space. Yeah, kind of like this. And that's where close. Maybe I need to increase the thickness of that. Roll that. No. It's very difficult to deal when you have a limited size and space. Yeah. I just need to extend that and move it a bit there. So it should be something going like this, all right? So kind of a curvy things. Now, after that point, we should have something as well, a flat going to 0, because there is no other forces acting on that direction. So what's your maximum bending moment is happening at the fixed support, which is the minus 43.5 kilonewtons meters. And this is how the shape of the, we need maybe to just adjust that one. It's a bit tricky, this one is a bit because of the corner of it, and you get that one. So that's how it looks like. It's very different from the previous example. So I'm showing you the previous example. We have a support reaction. Here we didn't have a slope, therefore everything was going a slope in the bending moment diagram. But since we changed that 5 kilonewtons with a UDL, you see now things has changed completely, and there's still the answers. It's kind of following the same process, and you go through it. So try this, and then let me know if you have any questions. Thank you very much.